Hey everyone, I'm the CEO of timbr.ai. I've previously worked on big data and semantic web technologies, and I'm going to show you today how with Timber you can run graph algorithms on top of relational databases, mostly data warehouse and data lakes. So let's start from the gap. Why you cannot run graph algorithms today on your data warehouse or data lake? So the gap that we see today is that most data is stored in tables and is being models and tables and columns. Graph databases and knowledge graphs store information in a graph structure, but also give you a way to define type of relationships between all of your business entities. So if you're here on the left and your data is a table, for you to run graph algorithm, to understand what relationships I have in the data, you need to move and build a knowledge graph. Well, with Timber, we took an approach that was different from the current standards. We said, instead of creating a new database, let's see how we can connect to the existing table and columns, incorporate all the knowledge graph capabilities. So Timber essentially transform your existing databases into a knowledge graph. We connect to almost any database in the market. We build a virtual knowledge graph. Now, in this virtual knowledge graph, you can declare all of the relationships, even though there are different schemas, different tables, different databases. The process of building the knowledge graph is virtual, so you don't need to copy data. You can do it with SQL. So if you're already familiar on how to create a table, you already know how to create a knowledge graph with Timber. But if you prefer not to do it in SQL, we also can do it user interface. So we offer for domain experts or people who are familiar with a specific business logic and want to embed this in the knowledge graph, they can also do it. And with Timber, because we work with SQL, any analyst, business analyst, any graduate that finished university can easily already know how to work with Timber. So let me show you the benefits of moving from the relational model to a knowledge graph. So writing complex queries in SQL has been a tough job up until now. Let's take, for example, fraud detection. Writing fraud detection queries in SQL is very complex and hard to write, but also to maintain. So here on the left, you can see an example of a query without Timber, which is complex and hard because of all the relationship that exists in the data that you need to explicitly declare. But when you work with Timber, you still write the query in SQL, but you do it on the knowledge graph. So you don't work with table and columns, you work with business entities. Each business entity has its own properties, its own unique relationship that you can take advantage, and you can write those queries a lot more simpler and intuitive. The other benefit you get, it's not only in the query side, but also in the exploration side. Imagine that you have hundreds, thousands of tables, and you want to understand what relationships I have in my data warehouse or in my data lake. So Timber introduces graph exploration over relational database. Even if your table format is a table, you can still look at all of your data as one virtual graph. So you can start with one entity, for example, Samsung. You can see the relationships to Samsung Electronics, and you can see the subsidiary and the CEO, for example. And each node is based on the ontology that defines your business domain. Now, I said before that for each concept, you have the business properties and relationships. So here, right on the menu, you can see all the properties that were declared in the model, but also all the relationships. Now, each time you explore your data, an SQL query is run behind the scene. So your data is still stored where it is today. But what about graph algorithms? We thought we've been able to do graph traversals in SQL. We've introduced even a graph visualization on top of a relational database. But we thought that graph analytics and graph algorithms was missing for some type of queries that are impossible to write in SQL. For example, if I want to find similar products, similar customers, build community of sessions of specific communities of product types, I can do all of that with graph algorithms in graph databases, but not on my relational model. One of the most common things that I want to do is do link prediction. Try to predict what is the link between two entities. There is no operator in SQL, or there is no way to do that in the SQL language. This is why, with Timbr, we thought to incorporate inside the language itself. So what are the benefits of graph algorithms? First of all, you can enrich all of your data. For example, the link prediction. You can predict links that does not exist today in the data. We also introduced new query capabilities. Now you can do in SQL find similarity or ranking of a specific entity in your knowledge graph. This also allows you to discover and analyze patterns, communities. But what is the real benefit? The real benefit of our approach is that no expertise needed in graph theory. If you already know SQL, you know how to query tables, you already know how to do community, pattern detection, find similarity and ranking in SQL. Now let me show you the process of how we've done it. So how we did it. So Timbr actually integrated with the lead platforms that allow you to run graph algorithms. The most popular is NetworkX, which is a CPU Python library of graph algorithms. So if you want to run your graph algorithms using the most popular library, Timbr works with NetworkX to do the execution. If you want accelerated graph algorithms and leverage GPU to get very fast results, we also integrate with RapidSEO Graph. RapidSEO Graph benchmarks are very, very fast and allow you to do different type of workloads that doesn't require you to wait for the results of the graph algorithm. We also integrate with Apache Spark to allow you to do parallel computation. If you have big data, if you have hundreds of gigabytes, terabytes of data, and you need to run global graph algorithms, this is where we can integrate with GraphFrames, GraphX to run all of your graph algorithms in a scalable way. Even if your data grows in the future, Spark will be able to handle it. So let me talk a little bit about the architecture. So up until now, Timbr was connected to all of the databases. And for a user to run a query, instead of connecting directly to the database, he connected to Timbr Knowledge Graph. And we would know how to query the tables in each database. But with graph algorithms, you can actually now, the process is different. Timbr runs the query that is intended for the graph algorithm, runs the graph algorithm, and shows back to the user. So now the user can get the results of a graph algorithm directly when he works with the Timbr platform in SQL. The way we've introduced it is using table functions. So imagine that each graph algorithm is a function, but not a standard function in SQL. It's a virtual table that you can call as a function because you have results based on a specific query. And you can choose whatever platform is suited for you. You can choose Spark, you can choose RapidSEO Graph or NetworkX when you configure Timbr. But what is the biggest benefit in our approach is that now any BI tool, you can expose the data enrichment and all the insights you got from the graph algorithm directly to the business side. So you don't even have to know SQL. If I run a graph algorithm, the output, the enrichment, the insights that was generated from can be exposed to the whole enterprise using the standard BI tool that you already have. So I talked to you about the process, how we did it, and what libraries we can connect to. Let me show you a demo of how it really works. So we took a sample of a data warehouse that exists on Azure Synapse. It's the Azure hosted data warehouse. And we have information about customers. Let me, for example, query the data warehouse and show you a sample of customers. So we have the customer name, last name, gender, email address, all the information that is typical in a retail company that stores information about customers. We also have information about products. So now we can query the product table and get a list of all the products. So I get from the product ID, product name, description. You can get the manufacturer, the brand name, color, all the attributes you have of a product. But this, what makes this interesting is if we want to analyze the sales of all of my products and customers. So now I can go to this online sales table, and I can see for each customer which product he bought, at which price, if there was a discount, what date, and all of the typical values you have for a sale. Now, Timber connected to the data warehouse, and we modeled an ontology on top of it. So this is the Timber platform, and we only modeled the concepts that are relevant for our algorithms. In this example, we took the sales table, mapped it to the sales concept. We mapped the table of products to product concept and of customer. So we actually created a concept that also represents a customer. Now, for each one of them, I can see all the list of properties and all of the relationships. When we looked at the data warehouse previously, we didn't saw the relationship that exists between those tables. But this can be declared in Timber as part of the knowledge graph. So I can see the Timber has made a purchase. So now I can go and see sales. And I can see that sales has a relationship to a product and a customer. And if I go to product, I can see the relationship onto the sale. This is one way to explore it. Another one is I can just click on sales and say find relationships. And now I can see all of the relationships directly in my knowledge graph. Now, once we have that and we declare the relationships, we mapped all of our data that is relevant for the algorithm, then we can move to the SQL lab. The SQL lab allows you to look at all of the concepts in the ontology. So let's, for example, look at a sales concept. So we go to the Timber schema, and we can see, look for the sales concept. Here we can find all the properties of a sale. But if I want to look at all of the relationships, I can go to dtimber. Dtimbers allow me to look at a denormalized view of the same entity. So now I can go to sales, and now I can explore all of the relationships of a sale. So I can see that bought the same. I can go to the same product that was bought in a specific sale. I can go to a sale was made by a customer, or I can go to the product of that specific sale. So all of those relationships and any relationship declaring the ontology is available for any user who works with SQL. And this is the first step before we run our graph algorithms. We can see all the properties of an entity, all of the relationships, and now we can start building our graph algorithms. So how did we expose it? So Timber introduced a new schema called gtimber. Now in gtimber, you can select your graph algorithm that you're interested. For example, if I want to run Louvain for a algorithm, then I can see what are the results that is expected from that table function. So when I look at gtimber Louvain, I can see that the result is the ID, could be a customer ID, a product ID, and in which community this ID belongs to. If I look at, for example, a Jacquard similarity to find similar people, similar products, I can see I have the similarity, which basically says, is it similar or not? And I have the ID, which could be the product, and the similar one. So you have two entities and one similarity that gives you the similarity between them. You can also run PageRank, for example. Timber supports any graph algorithm that is supported by those libraries. So if you want a specific library, that if it's CU Graph, NetworkX, or Spark, this can be exposed virtually as part of Timber. Now, if I want to, for example, run a Jacquard, let's find similar customers based on products that they bought. So I previously saved some queries just to show you how it works. So I can find similar customers based on Jacquard. And now let me show you how it works. So we have the gtimber schema, we have the Jacquard table function. Now each algorithm receives three parameters. First is the ID, the first ID. Second is the second ID to build the graph. So basically you have two entities and a relationship between them. And you can declare a weight of that relationship. In this example, we're saying, give me a customer ID and give me customer ID who bought the same product. So we're looking about customers who bought the same product here. And I want to find how much products they've bought that is similar. So I group by and get the number of products that is shared by those two customers. Now, of course, I can run this query, and I will just get results of a customer ID, another customer ID, and the number of products that they share. And I can also run the graph algorithm to see whether they're similar or not. So just to give you an example of the results, then you can see that this customer bought the same customer as all of those. And it changes, like this customer bought, those 3 customers bought the same product, and so on. So let's run the Jacquard algorithm and see the results here. See how I can find now similar customers based on a purchase of products. So here is the results. We have a customer ID. First, I have a customer ID. I have the similar one, and I have the similarity between them. Similarity means that they bought the same product. And for each customer, you get which customer is similar to him. Now, there is no way for me to do this in SQL without applying a Jacquard similarity algorithm. Now, we can take these results. This is saved as a temp table or as a full table in the data warehouse. And now we can incorporate as part of the ontology. So we actually went and mapped one of those tables to the customer a concept and added this as a relationship. So now I have a relationship for a customer to a customer, and basically with a similar customer name. So how is this exposed to users? Let me show you. I'll go back to the saved queries. And now I can run, give me similar customers of Adam. For example, I'm interested in a specific customer ID. And now, because I introduced this as a relationship in the ontology, when I look at the metadata of a customer, I can see all the properties, but also the relationship. So now I have a relationship called similar customer. That this is the output of the Jacquard similarity algorithm. So let's run this query just to show you the results. So here, now for Adam, I can see, look, those customers are similar to him. So if they bought a product that Adam didn't buy, you should recommend the product that they bought to Adam. You can actually build a recommendation system now based on those results. Now let me show you a different algorithm. If you, for example, want to find community of customers, for example, based on of customer behavior or purchase frequency, we can now use the Louvain algorithm to detect communities of customers. Now, this is very similar to the Jacquard one. The only difference is the name of the algorithm you want to run. So here we are running the Louvain, and we can find for all of my customers which community they are. So let's run this query. So in this example, we're using a network X, but you can configure either one of the other platforms. So here for each customer, the ID now represents a customer. I see in which community he belongs to. Now this is also something that now I can integrate as part of the ontology. So when I go back to the ontology, you can see we already created a customer community concept, mapped the communities to it, and created a relationship between customer and customer community. So for each customer here, now I can find similar customers or find community of customers and start analyzing them. Let's see, for example, a query that leverages this. So I'll go back to the saved query, and I'll query all the customer communities based on the relationship we introduced in the ontology. So here, what are we interested in? So we start by the customer ID. We get the label, which represents the name of the customer. And we have we also want the gender and in which community that specific customer is. And we also query the timbr customer concept. And we want only customers that were identified in a specific community. So here I got the results. I got the customer ID, customer name, the gender, and the community ID. Now, all of this, what it actually does, it leverages the table that was created from the output. I can see what timbr actually sends to the data warehouse in order to identify which customer in which community he is. So as you can see, here we are doing join in order to understand for each customer in which community he is. So if you look at the tables, this is stored in a graph algorithms output schema. This is where Timbr stores the results. Now let's visualize it. Let's see how we can take this one step further. So here I got the results. I want to visualize them, so I can go to the Explore button. And now I can visualize all of my data. I see the customer ID, name, gender, and community. Let's change the visualization. Let's do, for example, a bar chart. Let's count all the customers in each community. Let's run the query. So, I did by customer ID, by community ID, sorry. Yes. So here I get count by community ID. Yeah. So here I have it. I have the community number. So I have 10 communities, and I can see for each one of them how many people are in it. We can even break this further by saying, look at the gender of each people in each community. So now we can see this is actually quite close, but in this community there is almost double males than female. We can also visualize it differently. If I want to stack them, then I can stack the bars, so I can easily understand how many of them are female and how many of them are males. So this is quite interesting. In the 7th community, there are more males than female, almost double. But in the 12th community, you can see it's the opposite. This allows you to understand better what are the relationship, how to classify, how to understand the relationship that exists in your data. By introducing graph algorithms, this is available not only to the technical people, to data scientists, but to the whole enterprise.
So I'm interested in the aspects related to the schema management, where when you build a knowledge graph, integrating different tables as you do in your system, how do you manage the ontology, like the common schema over your knowledge graph, where when all these tables might have different overlapping schemas that might be heterogeneous, like different names for the same source, different ways of structuring data. How do you handle that?
So in Timbr, once you introduce the ontology, you can map different sources to it. And in the mapping process, you can leverage SQL to clean the data, to transform the data. So if I have two tables, for example, that represents a customer, and with one I have a customer name, and in the other one I have a column called name, in the mapping step, you can transform the name of the column and give it a different alias to match it into a standardized meaning to the whole enterprise. And this is also true for relationships. Timbr supports one-to-many, many-to-many relationships, and you can declare the semantic name of each of those relationships in the knowledge graph.
Okay, so you're using SQL as the transformation and mapping language. That sounds great. And then another related question is now, how do you manage identity? How do you manage record linkage when you have different entities that represent the same person, for example, in different tables? How do you manage the construction there of that aggregated entity? So
one of the benefits of working with SQL and data warehouse and data lakes, they are well suited for aggregations. So if you want to do aggregations on top of the ontology and want to aggregate different sources, they are actually optimized to do it.
Okay, so that is happening on the data warehouse or the data lake, upstream from the import in Timbr.
Exactly. So in Timbr, it's just a virtual knowledge graph. You have all the definitions in the ontology, all the definitions of the mappings. And what we do, we just introduce a virtual SQL schema that you can query like it's just another schema in your data warehouse. So you don't need to see all the table and columns. You can see the ontology and work with that as an abstraction layer.
And I might have missed it. The ontology, how is it defined? How do you expect the user to define it?
So I think it's best if I'll show you an example. Maybe that will also be better for everyone. So let me share my screen. So in Timbr, you can define let's take for example the customer concept. So in Timbr, you can visually add more properties. You can see all the properties in the ontology, or you can create new ones. You can create the relationships directly in the user interface. So I can introduce a new relationship in the ontology. I can give it the name, the inverse name, the target concept, the properties on which this relationship is built on, and so on. This is one way you can model the whole ontology in Timbr. And of course, you have the inheritance that allows you to do the subclassing of concepts. Another option to do it is in using SQL statements. So here you can see the create statement of a concept in the ontology. So if you're familiar with the create table, this is just an extension of the create table, that instead of table you use concept, and we introduce the inherits as part of the SQL language. So you can define hierarchies and do the subclass in Timbr.
Okay, thank you. So ontologies are also represented in SQL. And do you allow the possibility to import ontologies from OWL, for example, like standard schemas, taxonomies from the web?
Yes. So Timbr is fully compatible with OWL. We implemented Timbr based on all the inference rules that exist in OWL, so you can take existing ontologies like DBpedia, like FIBO ontology, the financial ontology, and load them into Timbr, and make them available to SQL users as well.
Great. Olivier is asking, how do you call external functions in timbr.ai?
So those are not external functions, those are table functions. So the function is exposed as a table, as a virtual table, that you call it as a function. This is something that is part of the SQL standards. Some SQL databases also have table functions. But what we've done here, we took the algorithms and made them available as table functions. So the integration part between the relational and the graph algorithm library is based on those virtual table functions.
Okay.
No, it doesn't have to be in the underlying DB. So I saw Oliver also asked, do you need the feature in the underlying database? So no, you can have the feature exists in Network X, in CU Graph, or in Apache Spark. This is where the actual algorithm is being run in memory in one of those specific platforms.
Great.
No problem.
We actually just got a question from Jakub, who's asking if you consider a virtual KG being a stopgap before moving to a graph DB, or is there something inherent in SQL first virtual KGs that will be necessary for some time to come?
So when you talk about moving to a graph DB, you're actually talking about full materialization of your data to a new database. So you take data from the data warehouse and data lake, and you do ETL, and you materialize in a new graph DB. Well, Timbr also supports materialization. So Timbr is virtual. You start with a virtual knowledge graph, but for specific workloads, specific complex queries, you can materialize it in memory or inside the data warehouse or data lake. So you get better performance. So we don't see it as the first step. We see it as a complete different approach that doesn't require you to go full materialize from day one. You can still materialize for better performance, and you can still do graph traversals, graph algorithms, and there's no need to move all of your data from day one to a graph DB. There are scenarios like a transactional use cases that you need that graph DBs are well suited to handle. And Timbr is mostly used for analytics, for the analytics part.
Great.